So it's a little bit of a cliche, but our words cannot express what an honor it is to speak here in this celebration of the work of Professor Faltings. So his influence on the work that I've done, the humble work that I've done, has been enormous, inestimable. And earlier on, you heard him say that young people shouldn't follow him but do their own thing. I'm no longer young, but I'm younger than him. And I think given the breadth and depth of his work, it's been very hard to follow this advice somehow. I feel like I'm always chasing in the footsteps of Professor Faltings. The mission I was given with my talk was to give the mathematics that we've discussed today, all the wonderful stuff, and put it into a broader context for a general audience to some extent, and I was told to target university students. So the experts in the audience, this talk is not for you. So please leave if you don't like this kind of thing. Right. But given, so this is a brief outline of what I'm going to talk about, and given the mission I was I was assigned, it's hard not to start with this question, right? Why should we bother with Diophantine equation? And I hope you're not expecting an answer, because the only slide I prepared, in fact, in answer to this question, was this rather pretentious picture. Right? And I'm not sure exactly what I was trying to say with this picture. Yeah? Possibly I'm trying to say that the theory of Diophantine equations is like a black hole that sucks you in whether you like it or not. So maybe that's kind of an answer to this question of why, or maybe I'm giving a negative commentary that these are silly things to worry about or to be working on within the scheme of great challenges facing humanity. I don't know exactly what it is. Right? But nonetheless, I'll let you be entertained by this picture for a second and move on to the actual meat of the talk. And like other the speakers, in order to actually motivate the subject that we're discussing today, the motivation I'm hoping will emerge from the subsequent slides. I will start with an example, as one often does in mathematics. Many of the examples I'm going to discuss have come up in previous talks, but it doesn't hurt to see them several times. So my first example is from this book of Diophantus, whose name has come up many times. He was an Egyptian mathematician from around the 3rd century. And his book called the Arithmetica was extremely influential in European mathematics following the 17th century. The picture you're seeing is a cover of the 17th century Latin edition. And this was supposed to be the edition on which Fermat scribbled his conjectures, in the margin of whose pages Fermat scribbled his conjectures. But of course, it was influential in many other ways, especially in the development of algebra. So this book is made up of many questions, or actually problems to be solved. That's what you see when you go through the book. And one of the questions is the example that I'm talking about right now. It's from book 4, problem 24. And here it is. So if you read it together, the English translation, it says, to divide a given number into two numbers such that their product is a cube minus its side. If we read a problem like this, it's very hard to make sense of it, right? We're not used to this kind of problem posed in words. Historians call these rhetorical equations. They're actually equations, but rhetorical ones that you're supposed to solve. And if you write it in modern notation, it looks something like this. The given number, we're calling A for a second, you're supposed to divide it up into two parts that I'm calling Y and A minus Y. That's the other part, right? And then you're supposed to take the product of the two and write it as a cube minus its side. So you end up with that equation, which these days we can understand much better than the sentence. It's, by the way, a remarkable tribute to pedagogy and advancements in science that equation is easier than the sentence for us. Anyways, so that's what we're supposed to solve. To take a concrete version, you can take something like A equals 6. This is what comes out in Diophantus' book. Then you're supposed to solve that algebraic equation that I've just put up. What kind of solutions? Right? And you'll guess by the content of the previous lectures, but also Diophantus' book makes clear that he actually is interested in rational solutions. Right? So if we were doing this as a pedagogical lecture in a course, I would let you struggle a little bit and try to find a lot of rational solutions. This isn't quite the appropriate venue for that kind of an exercise. So I'll just remind you some of the very easy solutions. So I think you can easily check, any one of you, that these are actually solutions to the equation. The first coordinate is x and the second coordinate is y. And so in other words, we're solving this equation in an easy way by simply setting both sides equal to 0, right? Finding possibilities where x and y can be designed in such a way that both sides are 0. That's one way of solving the equation. But this is kind of boring, right? These equations, these solutions are boring. So here are some more for you. So here's one, here's another one, and here's an even more complicated one, right? So this way you can generate very complicated solutions to this equation. And in the book itself, Diophantus gives this equation. This is simpler than the ones I just showed you a moment ago, but it's already quite complicated. You might wonder, how does one find complicated solutions like this, right? So that's what I will explain to you right now, using a theory that's already been alluded to by previous lecturers. So the way of generating these complicated solutions, the reason for it is that there's actually an operation on the set of solutions. You take the solutions, in particular, if you have two solutions, P and Q, there's a way to construct another solution out of it. This is the binary operation on the set of solutions. And sometimes we look at it, we write it this way, P and Q going to some other solution called P plus Q. Right? So the fancy way of saying it these days is that the solutions to the equation admit the structure of an abelian group. There's an operation and that turns it into a group. So that's the first occurrence of the name of Abel, and I'll mention it many times in the course of this talk. So there is Abel for you. It is a abelian group using this operation. How does this operation go? I'll show you how it goes using a picture of the curve. Already, Anna and other people refer to the fact that we use geometric pictures in order to solve this kind of equation. So this is a very good example. So when you plot out in the real plane the locus of points x, y that satisfy that equation, you get a picture like this. So what we want to do is take 2 points on it. I'm calling them A and B now. Sorry, I should have called them P and Q, but if that doesn't bother you. And I want to figure out a way to do something with those 2 points and produce a third point, right? So I called it plus. So those of you who have studied some mathematics might be tempted to just add the vectors A and B, and that doesn't work. You can see why, because if you just add the vectors, there's no reason for that addition to land on the curve. I want a point on the curve, right? So instead, we do something more clever, and this is what we do. We draw the line through these 2 points, and it will happen that that line will intersect the curve at one other point. I'm calling that C. Right? You could just leave it there, but that's not what we do. We take that point C and reflect it through that horizontal line of symmetry, right? And send it to the other side. And we call that point A plus B. That's the operation on points. You do this for any 2 points. You can do it to the point itself. You can do A plus A as well, even if you don't have 2 points, even if you have just 1 point. What you can do, instead of adding the line through 2 points, I can take the tangent line through 1 point, right? See where it intersects the curve and do that reflection thing again. That's A plus A. Right? So that's the operation I was alluding to a moment ago. So let's see what happens in the example that we started out with. Oh, sorry, I forgot to say that it's a group, and those of you who know about groups will know that there are inverses. So for any point A, minus A is simply the point on the other side of this line of symmetry. That's by definition. Okay? Right. So if you started out with this boring solution 0, 6 to the previous equation, to Diophantus' equation, what happens when you add P to itself? You get that point minus 1 over 36, 1 over 216. And if you take 3 times P, you get that. 4 times P, you get that. Right? And so by using that operation, you can generate all these complicated solutions. That's how I found it. I computed myself on a calculator somehow, just for fun. It took a while. Well, myself on a calculator. That's a contradiction, isn't it? Anyway, but there you go. Nowadays, we're so used to calculator, it feels like I'm doing it myself if that's all I'm using. All right. So that's the explanation for these solutions. And Diophantus' solution, by the way, is obtained from the solution minus 1, 0 by adding it to itself, then reflecting it through the line of symmetry. Okay, good. Any questions at this point? This is a very natural operation. I hope it looks natural to you. And a very interesting fact about this is that, I should have asked you the question first. That's okay. You'll already have guessed from what was happening with the previous operation. There are actually infinitely many solutions to Diophantus' equation. You can see that the solutions will just keep getting more complicated as you keep adding the points, right? But in fact, even though that's true, any rational solution to the equation can be written in terms of 0, 6 and minus 1, 0, these boring solutions, simply by applying these geometric operations, applying this operation sufficiently many times, you can get any rational solution. So that's a theorem you can prove, and that's a very remarkable fact about the structure of the equation we're looking at. And in some sense, You might regard the solutions that we see displayed on the slide as imaginary solutions. Why? You see, because Diophantus would not have regarded those as solutions. They are negative numbers, they are zeros, things like that, right? And he doesn't like things like that. He wanted positive rational solutions. And those aren't the ones that are shown here on the slide, but in fact, all solutions can be obtained from these imaginary ones. That's also quite interesting. Right. Before moving on, let me introduce a slightly boring operation where we change variables, take the equation that we started out with, and put a negative on both sides, and then I complete the square on the left and absorb the negative into the variable on the right. And if we do that, we can do this change of variable and write it in this form. The reason I'm doing this is because when we write it this way, this is called an elliptic curve. You've already seen it in Anna's lecture and Professor Faltings' lecture as well. This is an example of an elliptic curve. So in other words, Diophantus' equation was just an elliptic curve in different variables. People sometimes say it's the first elliptic curve in history. Of course, when somebody says something is the first, you never take that seriously. Nonetheless, it's interesting that there was an elliptic curve that long ago studied by Diophantus, and it is also a so-called abelian variety of dimension 1, which that word you've also heard. Right? And so Abel has come up again. So there are a number of different reasons for thinking about, reminding ourselves of this terminology, because it also shows you this kind of great tradition of mathematics, right? That you can take an equation that was studied by Diophantus sometime around the 3rd century, and somehow we're expressing it in the language developed originating in Abel in the 19th century, about a 6,600-year span where mathematics continues to develop during that period, right? Number theory, algebra analysis, and so on. So I showed you that, started out the lecture with that funny picture by Matiyasevich. So here's a corny illustration by ChatGPT of illustrating the tradition of mathematics. Now, but it's also true that elliptic curves are actually the source of some of the most sophisticated computations in mathematics. And that's why I'm also starting with this example, because my title has said something about arithmetic geometry and computation. And some of the most interesting computations in mathematics occur with elliptic curves. I already shown you some when we were computing new points, but there are many more interesting computations one can do, which I'll get to with a brief review from a slightly more distant perspective of what elliptic curves were about. You've heard so many times that word today that maybe this review is unnecessary, but I'll do it anyway since I prepared it. So as you will have seen, an elliptic curve refers to an equation of this form: y squared equals x cubed plus ax plus b, where a and b are integers. There's a mild condition there that keeps that cubic from having multiple roots, that imposes a certain non-degeneracy to the equation. Well, you don't have to pay attention to that, because if you choose a and b randomly, it will always satisfy that equation. So generally, we are talking about equations y squared equals a cubed plus ax, x cubed plus ax plus b, and some sample plots are on the slide. And we are interested in rational solutions, right? So here are some examples. We've already seen examples, and this is the example we saw, in fact, in the coordinate change that I made at the end of the previous section, right? And I already indicated to you that this has, for example, infinitely many rational solutions. This is an equation, I think this came up as well, that was studied by Fermat. It takes a little bit of work to show it, but in fact, this one only has those 3 solutions. This might be a bit puzzling, because I showed you this way of generating new solutions out of old ones, right? So if you try to generate new solutions out of these 3, you'll find these 3 just circulating among themselves. That can happen as well. You don't necessarily get more solutions. It did work with the previous example. So this one was also studied by Fermat and mentioned by Anna, right? And so it has the solution 3, 5, as we saw, right? So 3 cubed is 27 minus 2 is 25, which is 5 squared. On the other hand, you also have solutions like this, more complicated solutions. And by now, in this case, you'll have guessed how I got this. I did this by applying the group law, doing these operations, right? Then that's how I generated these solutions. On the other hand, this equation has no rational solutions at all. That can happen. So all kinds of things can happen. When you study elliptic curves, you might have finitely many rational solutions, no solutions, or infinitely many solutions. By the way, I guess I should have said this earlier. You can see by this way of writing down the elliptic curve why it's hard to get rational solutions, right? Why? You might choose some x to be rational, right? But then y has to be rational once you've chosen x, right? But to get y out of x, you compute the thing on the right-hand side, and you have to take a square root. When you take the square root, mostly you don't end up with rational numbers, right? Okay, so that's the challenge, and so all kinds of things can happen. However, here's a kind of interesting theorem of Mordell that was again came up in the previous lecture, and this is the starting point of much interesting discussion about computation. Even though all these complicated patterns can occur, there is some way in which the problem of finding rational points on an elliptic curve is finite. It's essentially finite. In what sense? Well, so here's the theorem. I'm repeating again. Right? So if E is any elliptic curve, right, then there might be infinite set of solutions, there might be none. There's all kinds of things can happen, but regardless of what happens, there's always a finite set of solutions that generate all of the rest. Generate in what sense? You start with that finite set, and you keep applying these operations, you can get all of them. So that picture that we saw with Diophantus' equation is typical. That always happens with any elliptic curve. So in group theoretic language, I'm writing it this way, but if you don't know that, you don't have to worry about that too much. So rather, I'll repeat again, regardless of what the elliptic curve is, there's always a finite subset of generators from which you can get all solutions. So that's the essential finiteness of the arithmetic of elliptic curves. So as we saw, I already stated the fact that for Diophantus' equation, for example, there are two solutions. These are the new coordinates, right, out of which you can generate all the rest. Right? Now, let's move on to a more serious discussion of computation regarding elliptic curve. It seems as though this finite generation statement should more or less close the subject of elliptic curve. It seems like there's not much to do. There's a fairly well-defined finite problem associated with the elliptic curves. Right? So I've just written Mordell's theorem again. Right? The problem is that even though we know that this finite generating set for the whole set of rational solutions, it's very hard to compute that finite generating set. We don't know a perfect way of computing that generating set. And that is a subject of the conjecture of Birch-Swinnerton-Dyer, one of the very famous open problems of number theory and mathematics that asks you for an algorithmic computation of the set of generators for an elliptic curve. So in other words, it challenges you to construct a machine that takes an elliptic curve as an input and outputs a set of generators for the rational solutions. That's what the conjecture is about. Okay? So this is a very interesting computational problem. And the mysterious thing is, even though I've already expressed the fact that this is a very important open problem, right? It's a very curious fact that in practice, you can always do this. It's never a problem in practice. So what I'm showing you up there is a web page from something called the SAGE project. So it's a freely available software to download. I encourage all students to try this out if they're interested. And you can plug in any elliptic curve, and it will find the generators for you. So I did this before the lecture, right? So I plugged in some elliptic curve, and it found those generators. It always works in practice. There were two generators for that curve, for example. This took a little while because the coefficient is a little big, but some of the earlier elliptic curves with small coefficients, it will give you the generators instantaneously. Right? So, just to show you these examples again, that was the one we discussed before. For Fermat's curve, I guess I forgot to mention that this is actually the generator. All the rational points can be expressed as multiples of this one. So you might ask, as I'm posing on the slide over there, what is the point of this conjecture? What's going on? I said this is an important open problem, but there's software freely available on the internet that will just compute the generators for you. Are these mathematicians crazy? What's going on? Well, the point is that the BSE conjecture is actually used in the algorithm in some sense. The algorithm that's applied, that occurs in that program available online actually uses the conjecture. What do I mean by this? So I'll make this slightly more precise. So here's the picture. Right? So there already is an algorithm for computing the generating set of an elliptic curve. It's called the descent algorithm. The reason for this terminology is complicated. I'm not going to quite explain it. It's historical. It's a bit of a whimsical terminology. But what happens is that there is this algorithm which involves quite a bit of algebraic number theory. That if you feed it an elliptic curve, it will compute with the algorithm. And one of two things might happen. One is it might compute forever, actually. It might never stop this computation, this algorithm, right? Or it might stop, it might go down that vertical arrow and yield the set of generators. Either thing can happen. That's what the current state of the art of that algorithm is, that it might go along either direction, right? But in fact, the conjecture says that the descent algorithm always terminates. The right-hand side arrow will never happen. It will always come down and give you a set of generators. That's what the conjecture is actually about. So I will give you a brief sketch of how this goes in order not to make the discussion completely superficial. Right? So this is a sketch of how that algorithm goes. The starting point is to use this notion of, that's come up many times, the height of a rational number. So given a rational number S over R, by height I just mean the maximum of the size of the numerator and the denominator. Yeah. So this way, we know that if you bound the height, there are only finitely many rational numbers. So what we first do is we approximate the full set of solutions of the elliptic curve by only looking at those of height at most n for some given n. Right? So that's a finite set, you see, because we can all try all tuples of numbers, rational numbers, satisfying that height bound, plug it into the equation and see if it works or not. So this can be just computed. Yeah. This EQ subscript n, so the solutions of bounded height can be just computed. It might be tedious, but you can compute it. So what you get is this nested sequence of points of height at most 1, points of height at most 2, points of height at most 3, and so forth. And so increasing things, then more and more, better and better approximate the full set of solutions. Now, so this part is elementary. The next part is what requires a little bit more theory. So there's a computable group homomorphism from the set of rational number to a rather sophisticated number theoretic object called the Selmer group. That's constructed out of the torsion points of the elliptic curve. So computable here means that that target group is computable, and that map can be computed whenever you hand it a rational point. So that's a homomorphism that you use to run this algorithm. So given that, you compute the image of all these height-bounded approximation with respect to this homomorphism. So up to there, I didn't say much. But in fact, the other thing you can do is you can take this increasing sequence and supplement it by a decreasing sequence from the other side. That is, this thing I wrote as the Selmer group with a subscript 1. It contains a Selmer group with a subscript 2, 3, and so forth. These are also constructed out of more algebraic number theory using higher order torsion points of the elliptic curve, yielding a doubly nested sequence like this, one from below, one from above, right? That contains the image of the rational points in the middle. And the fact is, what makes this algorithm work in practice is the following fact. Yeah? If at any time this approximation from below equals the approximation from above, yeah, then it's a fact. You don't need any conjectures. In that case, the set of rational points of height bounded by n, if that happens for any n, that or a very straightforward modification can be used as a set of generators. So that's a fact. That's not a conjecture. But then Birch and Swinnerton-Dyer say that for any elliptic curve, eventually this upper approximation sequence equals the lower approximation sequence. It has to stop at some point. We don't know that will happen. It's not guaranteed to happen, but in practice it happens. And whenever that happens, we get a generating set. That's how it works. Now, that was a very brief and quick summary. And I expect that if you haven't seen it before, it won't make too much sense. And I will excuse myself by quoting authority from Peter Scholze, whose name has come up many times. He's a very brilliant mathematician of our times. In an interview with Deutsche Welle, he speaks about going to the lectures of Professor Faltings, and he said, "I used to go there as a student, and I would never understand anything." Right? But in hindsight, I feel like I learned so much during that time. There's this misconception that certain parts of lectures are pointless if you don't get it right away. So don't regard the previous slides as pointless. Right, so that's one point. I'm not trying to compare my lecture with, of course, Professor Faltings. Nonetheless, this is a very common experience that all students need to get used to. So this is for the young people as a little bit of inspiration. Right, and so emboldened by this quote from Scholze, I'll also show you this slightly sophisticated diagram, yeah, that involves rational numbers, p-adic numbers that have come up in previous lectures, and topology of the rational numbers, things like that, that fit into a very beautiful diagram, actually, that inspires the previous algorithm. Even though I'm not going to explain it at all, I tend to think that diagram is rather of high aesthetic value and worth seeing and eventually understanding. Okay. I will make a few more comments before leaving this subject of Birch-Swinnerton-Dyer conjecture. Yeah. This comment I've already made. Number theorists by now have run these algorithms on millions and millions of elliptic curves. I'm not sure exactly how many. I did ask an expert for an estimate, and they said maybe 10 million elliptic curves. This algorithm has been run, and it always works. It always stops and gives you a set of generators, right? So if you compare the conjecture to a theory of physics, right, you can regard it as correct. There's nothing to do. Right? So if you take Newton's equation of motion or something, you don't prove it, you just assume it and deduce various consequences, and you regard it as evidence for the correctness of the theory, right? And we regard it eventually as more or less true. That's the status of VST right now. It's certainly correct. Any experiment that we do on the computer will convince us that it's actually true. So to ask a slightly provocative question to my mathematician colleagues, because there are some in the audience, we could ask two questions. The first question is, do we really need to prove this? After all, it's already so useful as far as solving the equations are concerned. We don't need to prove it. It always works. What's to do? Right? So that's one question. And then the second question, which is somehow topical, right, is whether machines will eventually help us discover conjectures or theories of the nature I'm discussing right now. Right? Of course, there's a lot of discussion of whether machines can prove theorems. That's an interesting question, right? But somehow, from our point of view, coming up with these kind of useful theories that you can prove or not to some extent, right, is in some sense more important. Right. Finally, before leaving the conjecture altogether, I should mention that the BSD conjecture roughly comes in two parts, one of which was mentioned by Anna, and but this the one I'm referring to right now is sometimes also called the conjecture of Tate and Shafarevich, but it's also subsumed in the BSD conjecture. And unfortunately, the Clay Institute doesn't offer a large reward for this. The other part, you'll get $1 million if you solve it. For this, you get nothing, but that's also good since we're mathematicians. We don't care about money. Now, of course, the achievement we're trying to celebrate today is actually not elliptic curves, it's higher equations of higher degree. Right? So this, if you look at polynomial equations, right, in two variables, elliptic curves correspond to the case where you have degree 3. But if you have degree at least 4, we have this great theorem of Professor Faltings, right? That if you put in some mild non-degeneracy conditions corresponding to this higher genus business, in fact, the set of rational solutions is always finite. Yeah. So you might think there's nothing to do, right? The theorem is an incredible theorem that tells you that the solution set is finite. So what's there to do? Well, it turns out that this is even more difficult to compute than this BSD generating set, right? We don't have anything like this BSD machinery to even conjecturally compute the set of rational solutions. Even though it's said to be finite, to actually compute it is hard. Do you have a question? No? You can interrupt me with questions as well, by the way. So this computational problem, in other words, associated with higher degree equations, is still open, and it seems to be very difficult. One exercise, by the way, again, for the students, you might ask, why is it finite? This is somewhat a response to Professor Oh's question from earlier, right? So, well, for example, why doesn't this method of elliptic curves, of generating new solutions out of old ones work? That's a worthwhile exercise I'll leave to you. If you try to do that, you'll soon figure out why this higher degree creates difficulties of generating solutions. You'll also encounter some important theorems of geometry and at least one important theorem of algebra of arithmetic, right? So you really get a feeling for arithmetic geometry by trying to answer this question. Why do you expect this to be finite compared to the degree 3 case? Okay, so I'll leave that to you. To get a sense, anyways, of the difficulty, you can consider this equation, right? This is a version of the Fermat equation. You just divide by the z on the right side, and your Fermat equation turns out to be the same as the problem of finding rational solutions to this equation. So what happened here is that we knew some solutions for a very long time, right? But it was very hard to prove that there are no more. That, in fact, was the full solution set, but we didn't know for hundreds of years. And that's the typical situation with higher degree equation. So, for example, you can change this equation slightly to something like this. Many of you will spot immediately the solution x equals 1, y equals 1, right? But I doubt if even Professor Faltings know whether there are any more. It's very hard to check whether these kind of equations have solutions, more solutions, right? In other words, sometimes it's easy to show like this one. It's easy to show that there are no solutions. Sometimes the structure of the equations allow you to deduce emptiness of the solution set. But if there isn't an obvious reason for non-existence, like that one I wrote, the middle equation, where if there already is one solution, it's typically very hard to know whether or not there are more. That's that's pretty much the typical situation. So for example, here's another equation that I just wrote down randomly, right? So this has the solution 1, 1729. And I've been asking this question at lectures for about 3 years. I still don't know whether there are any other solutions. That's the typical situation with higher degree equations. All right. So in fact, I've already stated this problem, right, which I'm putting it as a theorem, but it's not. It's a conjecture that already Professor Faltings alluded to. One could ask for an effective version of the theorem that he proved. Namely, we want a terminating algorithm that will take a higher degree equation as an input, right, and print out the full rational solution set. So that's the effective, we could call it the effective Mordell problem, right? Or we could call it a putative effective halting theorem. And that I've been more or less working on this all my life. And I feel like we've made progress, but it's still regarded as a difficult problem. So in other words, we know it's finite, but find the finite set algorithmically as a function of the input. So I will show you also a small diagram, right? Which, of course, you're not expected to understand, but I also regard this as rather aesthetic. So this is supposed to be a methodology that generalizes the BST theory and program, right? And it involves, what it's really doing is replacing abelian homology groups by non-abelian fundamental groups, right? In order to implement, it's an attempt to find this terminating algorithm. So here I'm advertising a little bit of my own work. Sorry about that. But it did occur to me before this lecture that I should tell you that the right-hand vertical map is sometimes called the non-abelian Abel-Jacobi map. So there's Abel again, and I found I couldn't resist saying it because you have Abel and non-Abel in the same phrase, right? So that's kind of a curious combination. Right. I think I've said most of the stuff I had planned to say of any substance, but I will give you some general observations on Diophantine equations arising out of the previous discussion. Right? So first of all, we could ask, so I started out with a discussion of degree 3 equations, and then we referred to Professor Faltings' theorem for degree 4 and above. Right? What about degree 1 and 2? Well, within the context we're discussing today, you might see that degree 1 is not at all interesting. These are just linear equations. Those are easy to solve. And Anna, in her lecture, mentioned that degree 2 equations is actually quite an interesting theory. That's the theory of conics, right? And it's completely understood, right? But that also involves quite a bit of sophisticated theory and something called the Hasse principle that allows you to connect solutions in real numbers or all these terrible p-adic numbers to rational solutions. What about more variables? So far, I've been somehow boring you with these two variable equations. What's going on here, right? So the honest answer is that it's too difficult. Once we have three or more variables, except for very special situations, right? It's very, very difficult. Even though two variables are difficult also, right? If you add more variables, there's almost no systematic theory. There are great results like this theorem of Professor Faltings on subvarieties of abelian varieties that Anna referred to, right? But there's almost no theory that's even close to systematic if you increase the number of variables. So you might say, for people who think about this kind of thing, it's quite an embarrassing state of affairs. You know? So I should be embarrassed. Even you should be embarrassed to some extent, right? That it's in such a primitive state, this theory of Diophantine equations in more variables. Right. So why are these so difficult? Right? So I hesitated about this section because it's kind of very fluffy stuff to some extent, right? But nonetheless, I thought I should say, because also this was a lecture about the arithmetic geometry and computation, I thought I discussed this topic briefly because it's also very related to the question of computation. Well, in some sense, Diophantine equations are really universal mathematical problems. That's a very grand claim, right? What could I mean by this? There's some way in which almost any mathematical result or mathematical problem can be translated into a Diophantine equation. Yeah? How strange, right? Yeah? So let me explain this just a little bit. It's a slightly cryptic remark. But so I'll start with an example again, right? In order to illustrate, or to explain what I mean by this. Suppose you start with, say, kind of a random polynomial like this, t minus x squared minus y squared, right? I'm regarding that t as a kind of parameter. I'm going to change it in to various values like t equals 1, t equals 2. And for each of those values of t, I get a different equation. One can view it in this way. Okay, of course, I can view it as a three-variable equation, right? But I can also view it as a t-parameterized family of two-variable equations, right? And associated to the polynomial, I've defined this set of natural numbers, SF. These are those natural numbers where fn, x, y has an integral solution. Yeah? So I hope that's clear. So for example, oops, sorry, this was a mistake. This should have been 5. f5, x, y. So that's 5 minus x squared minus y squared equals 0. You can see that 2, 1 is a solution, right? Yeah? 2 squared plus 1 squared equals 5. So in fact, 5 belongs to this set SF. 3 does not belong to it. This takes a little bit of work to see, but 3 cannot be written as a sum of 2 squared. You have to do a little bit of computation, right? So 3 does not belong to this set. So in general, this is some random thing to do. I apologize for and ask for your patience. I'm going to explain this in a second. I started out with this random family of polynomials and define a set of natural numbers, those parameter values of t for which there are solutions. Right? Now, to use a little bit of theoretical computer science language, this set is something called a recursively enumerable set. That's what people call this in the theory of recursive functions or Turing machines. So in other words, this is a set that we can write a program to generate. It's easy to write down a program that will list exactly the elements of this set. So I'll describe you briefly how it goes. Right? So what you can do is you can look at triples of numbers. Look at it in 3 variables again, n, x, y, all inside the box of size n most k. Right? So you get larger and larger boxes, b1, b2, b3, right, which get larger and larger. And whenever we find a solution inside one of these boxes, we throw the first component into our set SF. You can see that this way, eventually all elements of SF will be generated. In other words, nothing that's not in SF will be thrown into our set, and any element of SF will eventually appear through this process. And any of you will be able to write down a program which actually generates this. So this is the sense in which this set is recursively enumerable. It's generated by a program. Right? And obviously, we can do this with any polynomial, in fact. Right? Take any polynomial where I put the first variable to be t and m more variables, and I look at those parameter values for which that equation has an integral solution. You can recursively enumerate the solution, the elements of SP in exactly the same way. Now, there was this quite remarkable theorem of Yuri Matiyasevich in the 1970s, right, in the early 70s. It was his PhD thesis, where he said, in fact, any recursively enumerable set is of this form. Any set of natural numbers that can be generated using a program, in fact, has an associated Diophantine equation. That was a rather surprising theorem, which addressed a challenge of Hilbert from earlier in the century. So to write it down more precisely, given any recursively enumerable set, no matter what it is, it doesn't have to have anything to do with Diophantine equation. There's always a polynomial with integer coefficients such that our set is exactly the parameter values for which the equation has a solution. So that's the theorem. There were lots of consequences for the theory of computation of this theorem, but for our purposes, it sort of illustrates this universal nature of Diophantine equations I was referring to, because this recursively enumerable set can be anything. So for example, it could be something like the set of primes, or we could take a complicated computer program, right? And also define RA to be those inputs for the program on which the program stops. Something completely random like this. There's always a Diophantine equation that will determine whether or not the program stops. So that kind of thing. So this kind of very general nature of recursively enumerable sets allowed people to reduce all kinds of mathematical problems to Diophantine equations. So for example, this requires quite a bit of work, but you can reduce the Riemann hypothesis to the unsolvability of some Diophantine equation, for example. Although I don't think that, I wouldn't recommend that you try to prove it that way, but nonetheless, in principle, you can reduce a whole load of mathematical problems to Diophantine equations. Maybe even more generally, sometimes people like this view that mathematics is just a formal system, right? That doing mathematics is just writing down a set of axioms as reducing consequences. I don't like that view, but some people like it. And but from that point of view, what we can do is we can take any kind of formal language you might use for this and write down, number all the sentences in degree, in length and complexity, something like this, right? And define R to be just those n's for which Pn is a theorem. Yeah? So that's a recursively enumerable set. Yeah, so there's a Diophantine equation whose solvability will tell you if any given Pn is true. Right? So in other words, any theorem can be reduced to a Diophantine equation in this way. Right? So again, I don't know if you subscribe to this view of mathematics or not, but still, it probably does give some hint on the answer to our question, right? Why Diophantine equations have to be difficult. Because so much of mathematics can just be reduced to Diophantine equations. Right, so you shouldn't take this portion too seriously, right? But it's interesting to think about. And Matiyasevich's theorem, of course, is serious mathematics, regardless of what philosophical interpretation you give of it. So a lecture like this about the context of Diophantine equation probably wouldn't be complete unless I said something about the future, right? So I will conclude with these comments that this conjecture of Birch-Swinnerton-Dyer, right? So this lecture is supposed to be somehow about computation, and that's why I've been emphasizing BSD. It's because it started out with some very simple-minded experiments on elliptic curves in the early 1960s with very primitive computers. So you will find it in the computing lab at Cambridge right now. So that's the EDSOC computer on the left. And that right-hand side, sorry, I wanted to give you a picture of that door, which is the original door to the mathematical laboratory where Birch and Swinnerton-Dyer were doing their computations, experiments. Yeah. But the only picture I had a picture of my son in it, so I'm inflicting that on you as well. But anyways, so it's very interesting that they were just doing this simple-minded computation and solutions of equations, elliptic curve equations over finite field, right? And finding patterns in the number of solutions. And that led to this conjecture and just an enormous amount of mathematics. And it's not just computational mathematics, as I've already indicated to some extent. The BSD conjecture, of course, involves a lot of computations and quite sophisticated computation, but it also intertwines with theories, concrete problems. There's a remarkable unity inside mathematics that started out with these simple experiments. The Grothendieck theory of motifs, parts of the Langlands program, certainly, the Diophantine equations, as well as very sophisticated theory of computational algebraic arithmetic geometry are comprised by this conjecture that started with these simple experiments. So nowadays, thinking about this question is that history, right? I was supposed to say something about the future, right? It's hard not to reflect that this was a remarkable development, but everything there was somehow linear and abelian. There's Abel again, right? There's a kind of the category of motives that this generates is a very linear theory, and the topology associated with it is an abelian theory in many ways, right? So it's hard not to speculate, for me anyways, that we are living in this era of extremely enhanced computation, right? So possibly, I like to believe that the enhanced computation will give us some hint on how to progress into a nonlinear theory involving non-abelian structure. You know, that diagram I showed you after the discussion about effective faulting theorem may be aided by the enhanced era of computation and moving beyond Abel to non-Abel. Right? Yeah, so if I say something like that, of course, you will ask questions like this, right? This is a very much a question of our times, of these times especially, very recently. We're all interested asking these questions. Can machines do mathematics? Of course, this isn't a good question. Of course, machines can do mathematics. What we'd like to know is what kind of mathematics can machines do? And that's very unclear at the moment, right? So there was this interview that Professor Faltings gave with Die Zeit, right? And he said he doesn't want machines to destroy his mathematics. So I asked ChatGPT to produce a picture of AI faultings, and that's what it did. So I'm afraid it doesn't do a very good job with this kind. It's very unimaginative somehow. Right? Nonetheless, I did think about this question. I am thinking about this question in relation to arithmetic geometry and computational arithmetic geometry. So I wanted to give some reflections on the question. Of course, I'm not going to answer it. By telling you a little bit more of this story. I was very pleased to see this coming up in Viescha's talk. We prepared this independently, but we both had this identical diagram almost, right? So what is this about? What was I trying to say by putting this timeline on the board, on the slide? Well, you see, what happened here is that Professor Faltings wrote that paper on p-adic Hodge theory in 1988. And what do those two arrows represent? That represents the efforts of all other arithmetic geometries to understand that paper. So, in other words, that paper took more than 20 years for us to fully understand. It was so rich with ideas, so many interesting structures suggested in that paper, it really took over than 20 years to understand. Over 20 years to understand. And in fact, the effort to understand it even resulted in another Fields Medal. so that last paper of Peter Scholze resulted in his Fields Medal, of course. So it's an incredibly rich set of ideas, with some of which were very, very hard to follow, right? So when I was first preparing this storyline, right, as an important part of what we've experienced in this reign of Professor Faltings over my lifetime, anyways, right? And somehow I wanted to say that I can't imagine AI producing this kind of process, right? It's not just a proof of a theorem, it's a process that's generated over decades by a given paper. So I couldn't imagine. So that's what I wanted to say. Then I thought about it a little bit more, and I went to another interview, but the end of the same interview with Die Zeit. And so let's read that together. So the interviewer asks, Terence Tao also says that while proofs ultimately matter, the process brings many insights. If AI simply puts a check mark next to a statement, we learn nothing from it. Then Professor Faltings replied, yes, it could be one day, I can't imitate his accent. So it could be that one day AI says, the Riemann hypothesis, one of the great unsolved problems in mathematics, is correct, but you are too stupid to understand the explanations. Yeah, so AI might say that. Right? That's true. I suspect that even if AI says that, we'll do something similar to this slide. AI might say this, give us catch-over proof, or we'll probably spend a lot of time trying to understand it in our own terms. And that statement itself might generate a lot of good mathematics. So that was another interesting aspect of thinking about this timeline. Right? But also, I suddenly realized this thing where, okay, this is the answer, but you're too stupid to understand. This was my experience with Professor Faltings. The first paper, he said, okay, here's the answer, but you're too stupid to understand. It took us 20 years to get to it, right? So in other words, he was not only generating all this great mathematics, he was preparing us for the next evolution of mathematics. Okay, thank you very much. Thank you.
Thank you very much, Minhyong. We have time for questions from the audience.
If the question is about AI, I probably won't know the answer.
No, my question is about you defined a group structure
An elliptic curve, yeah.
On elliptic curve. Is it possible to create a group structure on curves of degree higher
Excellent.
degree?
That was my exercise for you.
Yes, but the one you proposed, it's clear that it
try it out
work.
and see what happens. That's
Okay.
my response. Yeah, sorry, I'm not giving you the answer right now. Now, people have thought about whether you can put higher structure of some sort on the points of other equations, right? It doesn't quite work, but trying to figure out what goes wrong if you try to do it with a degree 4 equation is a very instructive exercise. So I do recommend that you try. Yeah, sorry. I'm trying to be at least a little pedagogical even in a lecture of this sort.
There's another question over there.
Thank you. You said we should not take your universality statements about Diophantine equations too seriously. I take it very seriously. I think it's a very interesting part of your talk. So I wonder,
I'm not saying it's not interesting. But
so I wonder, does it imply that there are Diophantine equations for which you probably cannot solve the problem of, I mean, where the solvability is undecidable?
Yes, it does
It's
imply
like
that.
no?
It does imply that. Yeah.
Okay,
That's one of the
okay,
implications.
okay.
There are undecidable Diophantine. In fact, people even have examples, I think, of many variables.
Any final question? Yeah.
Actually, I should refine my answer a little bit. When you say undecidable, you have to sort of decide, you have to first determine a set of axioms and rules of inference and things like that, right? So there's also a kind of meta theorem that says that if a specific equation is undecidable, then there are no solutions. So it's a slightly complicated, slightly subtle, this question.
Yeah, so thank you for beautiful talk. So I have a question about your first part. So the Birch-Swinnerton-Dyer conjecture. When you have this sequence from both sides, so does the conjecture, if we know it, tells you something how fast this thing will stabilize?
Very natural question, but no, it doesn't. In fact, but that's kind of interesting. And so it doesn't. It's this BSD algorithm, the descent algorithm I referred to earlier. If you put an elliptic curve in with coefficients that are about, say, even 50 digits long or something like this, right? Yeah, I think it will compute for a few days at least. It takes a long time, right? And maybe 50 digits just won't even work. I'm not completely sure. I'm not an expert on the actual computation. But if you put in about 15 digits, it will work, but it will take a few hours typically. So we don't have a priori bounds. And that's very interesting question. And that's very closely related to a question that was posed by Professor Faltings, whether one can a priori bound above the height of solutions. Right? So that's another type of effective Mordell problems one can pose, trying to ask for a priori bounds and trying to prove them. So so this is where we've differed a little bit. I'm sorry, I should, of course, respect whatever you say, but nonetheless, I've always thought that this is interesting. This focus just on a priori upper bounds for heights may not quite be the only viewpoint and may not even be the best viewpoint. Finding a terminating algorithm could be another goal, right? That even without a priori bounds, that's just as valuable. And that's what's indicated by the theory of elliptic curves anyway. So what I think is that the theory of higher degree equations should naturally generalize the theory of elliptic curves. It's just a matter of turning abelian into non-abelian. But it doesn't come with a priori bounds.
Thank you very much. I think we close this session now and thank all 4 speakers of the day.
Good. Thank you.